of the 17.6 MeV, 80% of the energy released in the reaction shows up as the kinetic energy of the neutron, which, having no electric charge and being gammas as massive as the hydrogen nuclei that created it, can escape the CNU without leaving its energy behind to help sustain the reaction or to generate X-rays for blast and fire. The only practical way to capture most of the fusion energy is to trap the neutrons inside a massive bottle of heavy materials such as lead, uranium, or plutonium. If the 14 MeV neutron is captured by uranium, a Vega isotope, 14 MeV is high enough to fission both 235U and 238U, or plutonium. The result is fission and the release of 180 MeV of fission energy, multiplying the energy output tenfold. For weapon use, fission is necessary to start fusion, helps to sustain fusion, and captures and multiplies the energy carried by the fusion neutrons. In the case of a neutron bomb, see below, the last mentioned factor does not apply, since the objective is to facilitate the escape of neutrons, rather than to use them to increase the weapon's raw power. Tritium production. An essential nuclear reaction is the one that creates tritium, or hydrogen-3. Tritium is employed in two ways. First, pure tritium gas is produced for placement inside the cores of boosted fission devices in order to increase the energy yields. This is especially so for the fission primaries of thermonuclear weapons. The second way is indirect, and takes advantage of the fact that the neutrons emitted by a supercritical fission spark plug in the secondary assembly of a two-stage thermonuclear bomb will produce tritium in situ when these neutrons collide with the lithium nuclei in the bomb's lithium deuteride fuel supply. Elemental gaseous tritium for fission primaries is also made by bombarding lithium-6, 6Li, with neutrons, N, only in a nuclear reactor. This neutron bombardment will cause the lithium-6 nucleus to split, producing an alpha particle, or helium-4, 4He, plus a triton, 3T, and energy SAD 15. The neutrons are supplied by the nuclear reactor in a way similar to production of plutonium-239Pu from 238U feedstock. Target rods of the 6Li feedstock are arranged around the uranium-fueled core, and are removed for processing once it has been calculated that most of the lithium nuclei have been transmuted to tritium. Of the four basic types of nuclear weapon, the first, pure fission, uses the first of the three nuclear reactions above. The second, fusion-boosted fission, uses the first two. The third, two-stage thermonuclear, uses all three. Pure fission weapons. The first task of a nuclear weapon design is to rapidly assemble a supercritical mass of fissile, weapon-grade, uranium or plutonium. A supercritical mass is one in which the percentage of fission-produced neutrons captured by other neighboring fissile nuclei is large enough that each fission event, on average, causes more than one follow-on fission event. Neutrons released by the first fission events induce subsequent fission events at an exponentially accelerating rate. Each follow-on fissioning continues a sequence of these reactions that works its way throughout the supercritical mass of fuel nuclei. This process is conceived and described colloquially as the nuclear chain reaction. To start the chain reaction in a supercritical assembly, at least one free neutron must be injected and collide with a fissile fuel nucleus. The neutron joins with the nucleus, technically a fusion event, and destabilizes the nucleus, which explodes into two middleweight nuclear fragments, from the severing of the strong nuclear force holding the mutually repulsive protons together, plus two or three free neutrons. These race away and collide with neighboring fuel nuclei. This process repeats over and over until the fuel assembly goes subcritical, from thermal expansion, after which the chain reaction shuts down because the daughter neutrons can no longer find new fuel nuclei to hit before escaping the less dense fuel mass. Each following fission event in the chain approximately doubles the neutron population, net, after losses due to some neutrons escaping the fuel mass, and others that collide with any non-fuel impurity nuclei present. For the gun assembly method, see below, of supercritical mass formation, the fuel itself can be relied upon to initiate the chain reaction. This is because even the best weapon-grade uranium contains a significant number of 238U nuclei. These are susceptible to spontaneous fission events, which occur randomly. It is a quantum mechanical phenomenon. Because the fissile material in a gun-assembled critical mass is not compressed, the design need only ensure the two subcritical masses remain close enough to each other long enough that a 238U spontaneous fission will occur while the weapon is in the vicinity of the target. This is not difficult to arrange as it takes but a second or two in a typical size fuel mass for this to occur. Still, many such bombs meant for delivery by air, gravity bomb, artillery shell or rocket, use injected neutrons to gain finer control over the exact detonation altitude, important for the destructive effectiveness of airbursts. This condition of spontaneous fission highlights the necessity to assemble the supercritical mass of fuel very rapidly. The time required to accomplish this is called the weapon's critical insertion time. If spontaneous fission were to occur when the supercritical mass was only partially assembled, the chain reaction would begin prematurely. Neutron losses through the void between the two subcritical masses, gun assembly, or the voids between not fully compressed fuel nuclei, implosion assembly, would sap the bomb of the number of fission events needed to attain the full design yield. Additionally, heat resulting from the fissions that do occur will work against the continued assembly of the supercritical mass, from thermal expansion of the fuel. This failure is called pre-detonation. The resulting explosion would be called a fizzle by bomb engineers and weapon users. Plutonium's high rate of spontaneous fission makes uranium fuel a necessity for gun-assembled bombs with their much greater insertion time and much greater mass of fuel required. Because of the lack of fuel compression, there is another source of free neutrons that can spoil a fission explosion. All uranium and plutonium nuclei have a decay mode that results in energetic alpha particles. If the fuel mass contains impurity elements of low atomic number, Z, these charged alphas can penetrate the Coulomb barrier of these impurity nuclei and undergo a reaction that yields a free neutron. The rate of alpha emission of fissile nuclei is 1 to 2 million times that of spontaneous fission, so weapon engineers are careful to use fuel of high purity. Fission weapons used in the vicinity of other nuclear explosions must be protected from the intrusion of free neutrons from outside. Such shielding material will almost always be penetrated, however, if the outside e-neutron flux is intense enough. When a weapon misfires or fizzles because of the effects of other nuclear detonations, it is called nuclear fratricide. For the implosion assembled design, once the critical mass is assembled to maximum density, a burst of neutrons must be supplied to start the chain reaction. Early weapons used a modulated neutron generator codenamed Urchin inside the pit containing polonium-210 and beryllium separated by a thin barrier. Implosion of the pit crushes the neutron generator, mixing the two metals, thereby allowing alpha particles from the polonium to interact with beryllium to produce free neutrons. In modern weapons, the neutron generator is a high-voltage vacuum tube containing a particle accelerator which bombards a deuterium/tritium metal hydride target with deuterium and tritium ions. The resulting small-scale fusion produces neutrons at a protected location outside the physics package, from which they penetrate the pit. This method allows better timing of the first fission events in the chain reaction, which optimally should occur at the point of maximum compression/supercriticality. Timing of the neutron injection is a more important parameter than the number of neutrons injected. The first generations of the chain reaction are vastly more effective due to the exponential function by which neutron multiplication evolves. The critical mass of an uncompressed sphere of bare metal is 50 kilograms, 110 pound, for uranium-235 and 16 kilograms, 35 pound, for delta-phase plutonium-239. In practical applications, the amount of material required for criticality is modified by shape, purity, density, and the proximity to neutron-reflecting material, all of which affect the escape or capture of neutrons. To avoid a premature chain reaction during handling, the fissile material in the weapon must be kept subcritical. It may consist of one or more components containing less than one uncompressed critical mass each. A thin hollow shell can have more than the bare sphere critical mass, as can a cylinder, which can be arbitrarily long without ever reaching criticality. Another method of reducing criticality risk is to incorporate a material with a large cross-section for neutron capture, such as boron, specifically 10B comprising 20% of natural boron. Naturally, this neutron absorber must be removed before the weapon is detonated. This is easy for a gun-assembled bomb. The projectile mass simply shoves the absorber out of the void between the two subcritical masses by the force of its motion. The use of plutonium affects weapon design due to its high rate of alpha emission. This results in pure metal spontaneously producing significant heat. A 5 kilogram mass produces 9.68 watts of thermal power. Such a piece would feel warm to the touch, which is no problem if that heat is dissipated promptly and not allowed to build up the temperature. But this is a problem inside a nuclear bomb. For this reason, bombs using pure fuel use aluminum parts to wick away the excess heat, and this complicates bomb design because oil plays no active role in the explosion processes. A tamper is an optional layer of dense material surrounding the fissile material. Due to its inertia, it delays thermal expansion of the fissioning fuel mass, keeping it supercritical for longer. Often the same layer serves both as tamper and as neutron reflector. Gun type assembly. Diagram of a gun-type fission weapon. Little Boy. The Hiroshima bomb used 64 kilogram, 141 pound, of uranium with an average enrichment of around 80%, or 51 kilograms, 112 pound, of uranium-235, just about the bare metal critical mass. See Little Boy article for a detailed drawing. When assembled inside its tamper forward/reflector of tungsten carbide, the 64 kilograms, 141 pound, was more than twice a critical mass. Before the detonation, the uranium-235 was formed into two subcritical pieces, one of which was later fired down a gun barrel to join the other, starting the nuclear explosion. Analysis housed that less than 2% of the uranium mass underwent fission. Winking sad smiley 16. The remainder, representing most of the entire wartime output of the giant Y-12 factories at Oak Ridge, scattered uselessly. 17. The inefficiency was caused by the speed with which the uncompressed fissioning uranium expanded and became subcritical by virtue of decreased density. Despite its inefficiency, this design, because of its shape, was adapted for use in small diameter, cylindrical artillery shells, a gun-type warhead fired from the barrel of a much larger gun. Such warheads were deployed by the United States until 1992, accounting for a significant fraction of the 235U in the arsenal, and were some of the first weapons dismantled to comply with treaties limiting warhead numbers. The rationale for this decision was undoubtedly a combination of the lower yield and grave safety issues associated with the gun-type design implosion type. For both the Trinity device and the Fat Man, the Nagasaki bomb, nearly identical plutonium fission trough implosion designs were used. The Fat Man device specifically used 6.2 kilograms, 14 pound, about 315 the 12 USF ounce in volume, of Pu-239, which is only 41% of their sphere critical mass. See Fat Man article for a detailed drawing. Surrounded by a U-238 reflector /Tampa, the Fat Man's pit was brought closer to critical mass by the neutron reflecting properties of Fu-238. During detonation, criticality was achieved by implosion. The plutonium